Alrighty, welcome back, and welcome to lecture number 3 in the lecture series. Hopefully up to this point you're pretty comfortable with R, and even a lot of the basics of R, like using vectors, using the data frame, understanding what the matrix is, etc., etc. In this lecture, our goal is to talk about the basics of R plotting, so we'll make pie charts and bar plots and all of that good stuff. And we'll also talk a little bit about summary statistics. So I think this video is going to be broken up into two parts. The first part will be just on the plotting, and the second part will be on the summary stats. So if you're following along with the text-based walkthrough, that will probably include everything, but we'll probably cut it about halfway with the video. But enough of that being said, let's go ahead and get a new file going. We'll just grab a new R script and go ahead and save it as plotting and summary stats.r. Sounds like a good name to me. And just like we talked about in the last lecture, we really should get in the habit of putting the comments at the top of our code. So your name, the date, 2022, your email, well, it's turning into a typing exercise for me, isn't it? And then more or less the purpose of this script. So we'll just walk through some plotting and summary stats basics. Of course, this will be a little bit more meaningful when you're writing your own analyses, either in your work or for your research, but definitely it's best to get in the habit of doing that now. So let's load up the data. And we're going to be using the same data set that we used at the end of lecture number 2, the Phillips et al. Turtles data set. So hopefully you got any kinks worked out that you needed to so that you could appropriately load that up into R, because that's what we're going to do right now. So we'll make an object called turtles, which will be our data frame. And we'll read in the data using read.csv. And so long as this new R script that you just created is in the same folder as the Phillips et al. Data, you should just be able to load it up just like that with the tab autocomplete. Let's just check the head of turtles, the data frame, just to make sure that we're looking at what we hope we are, and it looks good to me. So just as a quick reminder of this, what this data frame is, we have, of course, observations of turtles by the year, and so we have the year and the species that was observed. And we also have this variable SCL. So I've got a little image that kind of describes what the SCL is, but it stands for straight carapace length. So essentially measuring the turtle's shell from sort of where the base of his neck would be down to the apex of the shell, that's the straight carapace length. The measurements that are in this data set are in centimeters. So this guy was almost 76 centimeters long. If you think about that, that's a pretty big turtle, actually. This guy was 80.2 centimeters long, etc., etc. So it's important to know kind of what the data is that we're working with as we kind of go forward. But I would also like to draw your attention to sort of the data types that we have in each one of these variables. So SCL, let's take a little bit deeper look. Let's get some more values. We can access SCL by first calling the data frame, turtles. And if we remember back to the second lecture, we used the $sign to access a single column or single variable in there. So the turtles $sign SCL. And I don't want to print out all 13,000 observations, so let's just say maybe 1 through 50. We'll index that with some indexing. So these are the first 50 observations of that. And we can see numbers approximately from maybe 76 is the lowest to 86 more or less is the highest in this first portion of the data set. But one thing I want to draw your attention to is that it's a continuous numeric data type, meaning it's not relegated to just a small number of values. It kind of could be potentially any value. If you think about it, you could have a really small turtle, or you could have a very large value for that. We'll see in just a minute that that's not quite the case. This is pretty normally distributed, but potentially any of those values from 0 to infinity could be the size of your turtle. Contrast that with, of course, the species, turtles, $species, where we are constrained, I suppose you could say, to just two values. It's either C Caretta or C minus. It's nothing outside of those two values. So let's get into plotting. I mentioned those data types because they'll be important as we're deciding what plots we use to represent the data, for example. One of the best plots to use to represent a continuous numeric data type like the straight carapace length is, that variable, is the histogram. So we can create a histogram by using the hist function, and the only parameter that's required for the hist function is just the data that it needs to look at. So we'll feed it the data turtles $SCL, because that's our continuous numeric data type, right? If we hit Control Enter there, we get our histogram. And like I said before, it's more or less normally distributed. We'll get more into that in the next couple of lectures. But the basic anatomy of this histogram is that the observations are sort of grouped up. So anything that was from 75 centimeters to 80 centimeters is in this group here. And the height of that group, that height of that bar, if you will, is the number of those observations, or the frequency. So we can see, for example, that between 90 and 95 centimeters, we had the greatest number of those observations. This also happens to be the mean or the median, I believe, happens to fall within this range as well. And that's the greatest number of observations in any of these groups. Now, take this plot. Every time I make a plot in R, I take it and I say, would I see this in some sort of publication or some sort of textbook or something? The answer to me is probably not. This turtles $SCL probably makes good sense to you and I who just wrote this, and we understand that that's the variable that we fed the histogram function. But it probably doesn't make good sense to somebody reading a textbook, for example. The same goes to say about the X label here, turtles $SCL. Doesn't make good sense to somebody who didn't write this script. So we can change those parameters, or those portions of the histogram. The name can be changed, or the title can be changed with main. And we can just say main equals, and it requires a character string data type. So let's just call it the distribution of turtle sizes. Let's just hit Control Enter and just see what changes. Of course, just the main title. And the X label, that labels the X-axis, can be changed with the parameter xlab equals, and let's just say the straight carapace length. Now, it'd probably be more informative. Of course, this depends on what your data is and what you know about the data, for example, but to put on a unit of measure there for centimeters, because, of course, we're talking about a turtle that measures 90 centimeters in length, for example. Now, this plot doesn't look too bad, actually. If you were to ask me, that is probably something you could probably see in a publication somewhere. Now, one question that we often have is how do we get this out? Say that I am writing a publication and I need to put this in my paper, right? How do I get this out of R and usable elsewhere? We can do so using the function JPEG, for example, if we want a JPEG image type. And so we would use JPEG. And the parameter that I give JPEG is a string, or a character data type, that contains the name of the file that we want to save to. So turtles histogram .jpg might be a good name for this. And what we're going to do is actually surround the histogram function with this JPEG function, and one more that says that is dev.off. So we won't get into the nitty-gritty of this necessarily, but you can think of this as this JPEG function opens up a file. The histogram then, as long as the JPEG function is open, the histogram function will write the histogram to it, and then dev.off just closes that file so that we don't write more stuff to it and make it look bad, essentially. But the general idea here is to wrap this with the JPEG and the dev.off. So let's just run these three lines all at once. Control Enter after we've highlighted them. Or you can, technically you could run them one at a time as well. It'll give you the same result. But let's go looking in our files. This is the same folder where I have my plotting and summary stats. It's right here, plotting and summary stats. And I'm looking for turtles histogram.jpg. And that is the exact same file, or the exact same plot I was just looking at in the plot viewer. Straight carapace length is centimeters and the appropriate title, and it looks pretty good. So then, of course, this is now saved on my computer. I can use it for anything else that I need it for. I will just stop here too and say that if, for example, you're not sure how to change a specific parameter, like you forgot how to change the main title, you can just type out hist, the function, put your cursor in the middle of the parentheses, and hit tab. And this will come up usually with a number of arguments. If that doesn't give you arguments, like that's not giving it to me now for some reason, you can do $hist, and it'll give you a little bit more help in this window here. So for example, hist, we have main right here. We have the X limit, the X label, the axes, etc., are all sorts of parameters that you can use to really customize the way that your histogram looks. So if it doesn't look quite the way that you want it to, take a look at these parameters and see if there's some parameter that you can change to make it look the way you want it. Now we're going to look at the dot plot next, and the reason that I want to look at the dot plot next is because it's kind of the cousin of the histogram. So you can remember this is kind of a problem where everything's grouped together in this range of values. We kind of lose a little bit of the full understanding of our values when we group them together like this. This is kind of a low resolution view. We want a little bit higher resolution view where maybe for every decimal point between 80 and 90 we have a line, for example, or a dot plot. Now the dot plot is not included, the function for the dot plot is not included on the base R. So we need to import some additional functions, and we're going to install then our first R package. You'll probably remember back in the first couple of lectures I talked about CRAN, the servers for CRAN, host R itself, and all the packages associated with it. We're going to now download one of those packages to use. So we can do so using install.packages. And the package that we're looking for is called uppercase BHH2. Go ahead and run that. No, I don't want to restart R. And hopefully you don't see any errors down here. You should see the downloaded source packages are in some place on your computer. We can then use library BHH2. And what library BHH2 does is essentially it tells R, hey, we have this downloaded package that we just downloaded, and take a look at the functions that are there so that we can use those functions in this script. So the function that we're looking for is dot plot with a capital P. And interestingly enough, the parameters are very similar to all other plots. So we can kind of just copy and paste what we've just done with our histogram and put that in and take a look at the dot plot it produces. And again, we have the same main title that we just wrote up here on line 15 and the same X label, axis label that we just made. So a lot of the parameters between these plotting functions are very similar. Once you know one plotting function pretty well, they're pretty well generalizable to other plotting functions. So that's the dot plot. And congratulations on installing your first package, if that's the case. If you're having problems getting BHH2 running, you'll probably get some sort of error message down here. Copy it and just paste it in Google and see if somebody has the same error as you, and you can just kind of follow the steps that they use for troubleshooting that. BHH2 is pretty broadly used though, and it's hosted by CRAN, so it should be pretty easy to install for you. Let's go on to the next one then, bar plot. So for some reason the dot plot didn't work for you and you've tried to work it out for a long time. That's okay. Let's just move on to the bar plot. Sometimes it's not worth pulling your hair out trying to get something to work when you could just ask somebody who knows a little bit more about it than you, and they can get it really quick just because of experience. So let's move on. I digress to the bar plot. So the bar plot, think about the bar plots that you've seen, and then think about our data. What sort of data in our data would you plot with a bar plot? I can think of one, for example, the counts of the different types of species, or the counts for each individual species. So how many times did we find sea caretta in the wild and measure it? How many times did we find the Atlantic green sea turtle in the wild and measure it, for example? So we can get those counts by using a function called table. And then if we give it the turtle's $species, what we have returned back is this labeled table of C. caretta was observed close to 10,000 times, and C. mitis was observed about 3,400 times. And we can feed this table. Well, let's go ahead and give this table a name before we use it. That's best practice. Let's just call this turtle table. We can put this turtle table into our bar plot function. And here we go. We've got our bar plot that represents the number of observations of each of our two species. Again, kind of like our histogram at the beginning, we're probably not winning any artistic awards for this plot, so let's go ahead and clean it up a little bit. The first kind of glaring problem here for me is this y-axis only goes up to 8,000, but we remember our C. caretta was close to 10,000. So let's start by fixing that. We can fix that by using the parameter ylim, and we actually give it a vector of just two values. One is the low extreme that you want, and one is the high extreme. So we'll say from 0 to 10,000. Take a look at how that changes our plot. Looks a little bit better. If we wanted to get rid of that ugly gray color, we could color this with COL. And again, we give another vector. The first item in the vector is going to be the first color that appears, so the one for C. caretta. Let's just put that in blue. And C. mitis, given that it's the Atlantic green sea turtle, let's just color it green. There we go. And those are just a couple of basics, of course, with the bar plot function. You can look through all of the different parameters. If you say question mark bar plot, for example, look at all those parameters and change whatever ones you'd like to make your bar plot look as you wish. We could, of course, put a main axis or a main title on here and stuff like that, but we'll save the time on the video. One other type of bar plot that we can do, this specific table that we use, the turtle table, let's just remind ourselves what it looked like. This is what we call a one-way table, where it's just the counts of one specific variable, one dimension, if you will. We can make another type of table that's called a two-way table. So let's see what that would look like in the code first, and then we'll explain it. Table, and let's say that we want turtles species by year. So the number of turtles that we observe every year, for example. Turtles $year. So we just separate those with a comma. And let's take a look at what our two-way table looks like. It's each species, how many observations it was for a given year. So in the year 2000, this group of scientists, measured 234 different C. caretta turtles. And they only observed 80 C. mitis turtles. I guess the next year they only observed 6. Maybe these are harder to find, or maybe they weren't looking for them very hard. Now let's make this two-way table into a variable. Two-way turtle table. Two-way turtle table. I didn't mean for this to be a tongue twister, but it ended up being that way, didn't it? And then let's look at a bar plot of our two-way turtle table. And here we are. Again, we're probably having a problem with the y limits here. We could probably fix that up. And also, I'm not quite sure what's going on. It's, I know from the tables that we looked at that there's more C Caretta by year than there is C Midas, so the darker is probably the C Caretta, but we should really add a legend that kind of describes what that is. So let's take care of the Y limits first. Oh, I don't know, what's this top one, maybe 1200? Should we go from 0 to 1200? If you can't see the top number, you can just stretch this out a little bit and you'll probably have it appear. 1200 is probably good, maybe 1000 was fine, but we'll just leave it as is. And let's add the legend. So we do so by saying, giving the parameter legend.text. And we'll give it a vector where the first text that we give it is for C Caretta and the second is for C Midas. So we'll just say C Caretta. And the second element in my vector here would be C Midas. That's not a bad place to put that, actually, in the top right. If you wanted to move that around, for example, over here to the top left, we can do so by saying args.legend. And this is one that, eventually you'll memorize, but for the first little bit, I don't know how they come up with args.legend argument being this way, but you say list x equals top left. So there's no way that I can break this down aside from saying that's just the way that the developers of this function made it. So args.legend, sorry, I'll stop jumping my screen around. Args.legend equals list x equals top left. There's other args that you can put into args.legend, but location is the one that I use the most. If we wanted to make this look a little less boring, of course, colors. Let's just make things blue and green again. Looks like a Teenage Mutant Ninja Turtle now. And we can even give the function, or the parameter beside, equals true. And that will put everything side by side as opposed to on top of each other. I kind of favored this original view, though. Looks like something from a comic book to me. So, all right. That'll do for a bar plot. I want to go back to our turtle table, though, because we're going to talk about pie charts next. So the pie chart is essentially just a chart that shows the percentages, if you will, or the proportions of each turtle. So going back to our turtle table one more time. These are just the raw counts. But what if I wanted to turn these into percentages? So what percentage of the observed turtles were C Caretta versus C Midas? I can do so by using prop table. And then I give it the turtle table. And now I have the proportions. So I'll just call this proportions. And I can make a pie of the proportions. Here we are. Now, just as with a lot of the other plotting functions, a lot of these arguments are the same. So we could say main equals title, for example. And we can even change colors and manipulate this however I would like. For brevity's sake, we'll let you play around with the arguments there. Now, for the last thing that I'd like to touch on in the plotting first section of this lecture is the box plot. So what I want to introduce now is the code that we write to make the box plot. What I'll talk about in the next lecture, or the next part of this lecture rather, is sort of the theory behind the box plot and what statistics are plotted, etc., etc. I feel like the rest of these plots are pretty straightforward, but the box plot does deserve special attention because of the statistics that it represents. So to make a box plot, we're going to plot a continuous numerical data type. So we just use the function box plot. And the only continuous numerical variable that we have in our data set is our turtle's SCL, straight carapace length. So we'll get way more into the details of what this box plot means in just a moment in the next video, but we have the median here, And we can kind of get a sense of the distribution of this data here too. A couple of functions or a couple of parameters that are useful here. We could say horizontal equals true, for example, and get a horizontal box plot. And of course, you can color it. You can add a main. You can add an X label, for example, etc., etc. So the sky's the limit on these plotting functions, and we really just want to give you the basics so that you can make your own plots, and then let you know that those parameters are there so that you can change whatever parameters you want to in the future. We'll leave it there for this first half of the lecture, and in the next half we'll delve way more deeper into these box plots, the anatomy, and sort of what each one of these lines represents. Thanks for watching.